Now in this lecture we'll answer on two questions. In the first question we'll find out the area of this green shape that is inside square ABCD, and in the second question we'll find out the area of this green shape that is inside quarter circle AOB. So we'll start with the first question. In the drawing we have square ABCD. We know that this is angle PQC, that is a right angle. Line segment PQ equals to 2 units in its length. Line segment QC equals to 4 units in its length. Again, our mission is to find out the area of this green shape. That is actually the area of quadrilateral PQCD. So first of all, we know that all the angles inside any square are right angles. So those two angles are all right angles. So write it down. This is a right angle. This is also a right angle. This is a right angle. And finally, this is also a right angle. We define one side of this square ABCD as A. So all the four sides must be also equal to A. That is to say, this is side AD. According to our definition, side AD equals to A units in its length. This is side AB. It is also equals to A units in its length. This is side BC, that is equals to A units. And this is side DC, that is also equals to A units in its length. In the next step, we define the length of this line segment QB as X. What is the length of the missing line segment AQ? From the drawing it is very easy to see that AQ equals to AB minus QB. So write it down. AQ equals to AB minus QB. So AQ in total equals to AB, that is A according to our definition, minus QB, that is X according to our definition also. So in total AQ equals to A minus 6 units in its length. This is side AQ, that is equals to A minus X units in its length. In the next step, we define this angle DCB as alpha, and we focus on the right triangle QBC. Right triangle QBC. This angle equals to alpha, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side of square ABCD, therefore it is absolutely a straight line. So AB is a straight line, so if you focus on this side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to the rule 3 that states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of AB at point Q? We have this angle that is 90 degrees minus alpha. This angle is 90 degrees, therefore this missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles on one side of a straight line according to rule 3. Therefore this missing angle must be equal to alpha. In the next step we will focus on the right angle QAP. In the right angle QP, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this previous angle must be equal to 90 degrees from alpha. According to the rule, the sum of the angles in any triangle is equal to 180 degrees. So in the next step, I will copy this right triangle APQ and this right triangle QBC in the new page, and we will prove that those two right triangles similar to each other according to angle similarity rule. So actually those are the two right triangles. This is triangle APQ and this is triangle QBC that I copied from the original drawing. So in the next step we'll prove that those two right triangles are similar to each other according to angle rule. So here this right triangle QBC. This angle equals to 90 degrees minus alpha, and this angle equals to alpha. So, why those two right angles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So actually, this is angle AQP. In the right triangle APQ, and it is equals to this angle, that is actually angle QCB. In the right triangle QBC. And again, angle AQP equals to angle QCB, they are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. So actually, this is angle QAP in the right triangle APQ, and it is equal to this angle. This is actually angle QBC in the right triangle BQC. So repeat again. Angle QAP in the right triangle APQ equals to angle QBC in the right triangle BQC. They are both equal to 90 degrees, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle APQ. In the right triangle APQ, and it is equal to this angle, this is actually angle BQC. In the right triangle QBC. So repeat again, we shall find out that angle APQ equals to angle BQC. D'abord equal to 90 degrees one side, therefore they are equal to each other. So we actually proved that all the figures on this right triangle APQ are correspondingly equal to all the figures in this right triangle QBC. And therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. So the right triangle APQ is similar. This is the sign of similar to the right triangle QBC according to angle similarity rule. And so the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AP, the right triangle APQ, over side QB in the right triangle QBC equals to side AQ in the right triangle APQ over side BC in the right triangle QBC. And it is also equals to side PQ in the right triangle APQ over side QC in the right triangle QBC. So if we again, we shall find out that according to equation 1, AP over QB equals to AQ over BC equals to PQ over QC. AP is the missing side, so we leave it as it is. Over QB. QB is x, therefore we substitute QB by x, and it is equals to AQ. AQ is A minus x, therefore we substitute AQ by A minus x over BC. BC is A. And it is equals to PQ, that is 2, over QC, that is 3. So now we found out that according to equation 1, AP over x equals to A minus x over A, and it is also equals to 2/3. So here, those two expressions are equal to each other, therefore we get equation 1 from those two expressions that are equal to each other. So according to equation 1, we get that AP over x equals to 2/3. It again, according to equation 1, AP over x equals to 2/3. 2/3. So here we multiply this equation 1 by x, and finally get that according to equation 1, AP equals to 2/3 x. So we found out that according to equation 1, AP equals to 2/3 x. So here those two expressions are also equal to each other, therefore we get equation 2 from those two expressions that are equal to each other. So according to equation 2, we get that a minus x over a equals to 2/3. So I write it down. According to equation 2, we should find out that a minus x over a equals to 2/3. Here, of course, multiply this equation 2, and finally get that according to equation 2, 3 times a minus x equals to 2a. We open the brackets on this side of this equation 2, and finally get that 3a minus 3x equals to 2a. Here subtract 2a from this equation 2, and finally get that according to equation 2, 3a minus 2a is a, so a minus 3x equals to 0. Here we add 3x to this equation 2, and finally get that according to equation 2, a equals to 3x. So if I found out that according to equation 2, a equals to 3x. In the next step, I'll copy this right triangle QBC in the new page and we'll implement the Pythagoras theorem on this right triangle QBC. So actually, this is the right triangle QBC that they're going from the original drawing. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle QBC is QC, therefore the square of the hypotenuse is QC squared, and QC squared equals to QB squared plus BC squared. So I write it down. This will be equation 3. So QC squared, that is the square of the hypotenuse, is equal to QB squared plus BC squared. QC is 3, therefore QC squared is 3 squared, that is 9. And it is equals to QB squared. QB is x, therefore QB squared is x squared plus BC squared. BC is a, therefore BC squared is a squared. So in total, we found out that according to equation 3, x squared plus a squared equals to 9. This is according to equation 3, but according to equation 2, we have already found out that a equals to 3x. If a equals to 3x, it means that a squared must be equal to 3x squared. Therefore, we substitute a squared in this equation 3 by 3x squared from equation 2. We do it now, we get that according to equation 3, 9 equals to x squared plus a squared. A squared is 3x squared, according to equation 2. This is plus 3x squared. So in total, according to equation 3, we found out that nine equals to x squared plus 3x squared. 3x squared is 9x squared. So in total, we found out that 9 equals to x squared plus 9x squared. This is to say, according to equation 3, 9 equals to x squared plus 9x squared is 10x squared. So according to equation 3, 9 equals to 10x squared. Here we divide this equation by 10. And you get that according to equation 3, x squared equals to 9 over 10. So here we take a root out of this equation, equation 3, and we get that according to equation 3, x equals to the square root of 9, that is 3, over square root of 10 units in its length. So today we found out that according to equation 3, x equals to 3 over square root of 10 units in its length. But according to equation 2, we found out that a equals to 3x. A equals to 3x, so a equals to 3 times x, and x is 3 over square root of 10. So today we found out that according to equation 2, a equals to 3x, and 3x equals to 3 times 3, that is 9 over square root of 10. In total, we found out that a equals to 9 over square root of 10 units in its length. So here we can write down that AB is equals to AB, and also DC that equals to A is equal to 9 over square root of 10 units in its length. Now the only thing that is left to do is to find out the value of AP. And according to equation 1, we already found out that AP equals to 2/3 x. And again, according to equation 1, we already found out that AP equals to 2/3 x. And AP equals to 2/3 x, this is to say, according to equation 1, AP equals to 2/3 times x. And we already found out that x equals to 3 over square root of 10. So in total, AP equals to, here we have 3 in the numerator, and 3 the numerator, so 3 we get cancelled. After we get the 3, we get that AP equals to 2 over square root of 10 units in its length. Again, AP equals to 2 over square root of 10 units in its length. So here, this is line 7 AP, that equals to 2 over square root of 10 units in its length. What is the length of line 7 PD? From the drawing, it is very easy to see that PD is equals to AD minus AP. So write it down. PD equals to AD minus AP. PD equals to AD, that is A, minus AP, that is 2 over square root of 10. So in total, if you found out that PD equals to A minus 2 over square root of 10 units in its length. So PD equals to, we already found out that A equals to 9 over square root of 10. So this expression in total equals to 9 over square root of 10 minus 2 over square root of 10. This actually equals to 7 over square root of 10. Okay. PD equals to 7 over square root of 10 units in its length. So I write it down. This is line 7 PD, that equals to 7 over square root of 10 units in its length. We join points P and C together by a straight line. By joining points P and C, we get that there are two right triangles. The right triangle PDC and this right triangle QPC. Our mission is to find out the area of this green shape. So what is the area of the green shape? So the area of the green shape is equal to, actually this green shape consists of those two right angles. Again, this green shape consists exactly those two right angles, the right angle PDC and this right angle PQC. And therefore, the area of this green shape must be equal to the sum of the areas of those two right angles, triangle PDC and this triangle, right, triangle PQC. So I write it now. So in total, we found out that the area of this green shape equals to the area of the right triangle PDC plus the area of this right triangle PQC. So in total, we found out that the area of the green shape is equal to the area of the right triangle PDC plus the area of the right triangle PQC. Well, because of the fact that this green shape consists exactly those two right triangles. And therefore, the area of the green shape must be equal to the area of those two right triangles. So what is the area of the right triangle PDC? What is the area of this right triangle PDC? The area of the right triangle PDC must be equal to the base of the right triangle PDC, that is PD, times the height, that is DC, divided by 2. And again, the area of the right triangle PDC equals to the base, that is PD, times the height, that is DC, over 2. Plus the area of this right triangle PQC. What is the area of the right triangle PQC? It is equal to the base of the triangle, that is PQ, times the height, that is QC, divided by 2. Well, repeat again, if we found out that the area of this right triangle PQC is equal to the base of the triangle, that is PQ, times the height, that is QC, divided by 2. So the area of the greenish shape in total must be equal to PD 7 over square root of 10 units for PT equals to 7 over square root of 10 units times DC. DC equals to 9 over square root of 10 units in step. This is to say, DC is one side of square ABCD. This is 8, so equals to 9 over square root of 10 units in its length. So in total, we found out that there are of this right triangle PDC is equals to the base of the triangle that is PD, and PD is 7 over square root of 10 times the I that is DC, and DC equals to A, and A equals to 9 over square root of 10 units in its length divided by 2. But there are the right triangle PQC. There are the right triangle PQC. There are this right triangle PQC equals to the base of the triangle that is PQ times the I that is QC over 2. So in total, if we found out the area of this right triangle PQC is equals to the base of the triangle that is PQ times the I that is QC divided by 2. So there are the green shape equals in total to there are the right triangle PDC. So it equals to, here we have 7 times 9, that is 63 over square root of 10 times square root of 10, that is 10 divided by 2. So this expression in total equals to 63 over 10 over 2 plus PQ, PQ is 2 times QC, QC is 3 divided by 2. So in total, if we found out that the area of the green shape equals to here we have 63 over 2, 63 over 10 over 2, 63 over 10 over 2 is equal to 63 over 10 times 2 plus 2 times 3, 2 times 3 over 2, 3 because 2 over 2 is 1, so total this expression equals to 3. So now the green shape in total equals to 63 over 2 times 2, that is 20. So it is 63 over 20 plus 3. So here we multiply 3 by 20 and then we divide it by 20 in order to confirm this number. So there the green shape in total equals to 63 plus 20 times 3 is 60 divided by 20. So in total there the green shape equals to 63 plus 60, that is 123 divided by 20. So if we found out that the area of this green shape is equal to either 123 over 20 square units, so in terms of numbers, the area of this green shape is equal to 6.15 square units. And again, the area of this green shape equals to either 123 over 20 square units, so in terms of numbers, the area of this green shape is equal to 6.15 square units. So if we finish with the first question, in the next step, I'll present to you the second question and we'll solve it. So our mission in this second question is to find out the area of this green shape. So in the drawing we have quarter circle AOB. We actually know the side in quarter circle AOB, arc AP equals to arc PQ equals to arc QB. In addition, we know that this angle AOB is a right angle. It is true in any quarter circle, and those two angles are also right angles. And we also know that OB equals to 5 units in its length. OB is the radius of this quarter circle, so we know that the radius of this quarter circle is equal to 5 units in its length. Again, our mission is to find out the area of this green shape. So we know that chord AP equals to chord PQ equals to chord QB. So here we can implement rule 20. So repeat quickly on rule 20. According to rule 20, in front of equal arcs there are equal central angles. So in the drawing we have a circle, and we also have, this is arc AB that is equal to this arc CD in its length. And according to this rule 20, because of the fact that arc AB equals to arc CD, in front of those two equal arcs we have equal central angles. So in front of this arc AB we have this central angle alpha, and in front of this arc CD we have this central angle beta. And according to this rule 20, they are equal to each other. That is to say, the size of the central angle alpha equals to the size of the central angle beta. That is to say, alpha equals to beta according to this rule 20. So we can implement rule 20 in our drawing. Now in our drawing, it is given us the question that arc AP equals to arc PQ equals to arc QB. So in the next step, we will join points O and P together by a straight line. And we also join points O and Q together by a straight line. So, because of the fact that it is given as a question that arc AP equals to arc PQ equals to arc QB, according to rule 20, in front of those three equal arcs we have equal central angles. So those three angles that are located in front, those three central angles that are located in front those equal arcs must be also equal to each other. So if this central angle AOP equals to x degrees in its sides, then according to rule 20, the size of this central angle P or Q must be also equal to x. Likewise, according to the same rule 20, the size of this central angle Q or B must be also equal to x units. So from one side, angle AOB equals to x plus x plus x, that is 3x, but from the other side, because of the fact that AOB is a quarter circle, this angle AOB must be also equal to 90 degrees in its side. So in total, we actually found out that angle AOB equals to 90 degrees from one side, but from the other side, angle AOB equals to 3x, and therefore we derive that 3x equals to 90 degrees. So I write it down. If we found out that 3x equals to 90 degrees, so here we divide this equation by 3 and finally get that x, the missing angle x equals to 90 degrees over 3, that is 30 degrees. So if we found out that the missing angle, the missing central angle AOP is equals to x, it is equals to 30 degrees in its size. Likewise, the missing central angle POQ that is also equals to x equals to 30 degrees, and finally the missing center angle QOB is equal to x is equal to 30 units, 30 degrees in its size. So in the next step, we'll focus on this right triangle, triangle MPO. The right triangle MPO, this angle equals to 30 degrees, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 60 degrees in its size. According to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. So according to the rule, we get that 60 degrees plus 30 degrees is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on the right triangle NQO. The right triangle NQO, this angle NOQ equals to 30 degrees plus 30 degrees, that is 60 degrees. This angle equals to 90 degrees, and therefore this first missing angle must be equal to 30 degrees in its size, according to the sum rule that states that the sum of the angles in any triangle is equal to 180 degrees. Okay, so in the next step, I'm copying the right triangle MOP and this right triangle NOQ in a new page, and we prove that those two right triangles can go into each other according to angle sine angle rule. So actually, those are the two right angles, MPO and NQO, that are copied from the original drawing. So in the next step, we'll prove that those two right angles can go into each other according to angle sine angle rule. So why those two right angles can go into each other? First of all, those two angles are both equal to 60 degrees, therefore they are equal to each other. So this is angle MPO. In the right triangle, MPO and is equal to this angle, this is actually angle NOQ. In the right triangle, NQO. So repeat again, we should find out that angle MPO in the right triangle MPO equals to angle NOQ in the right triangle NQO. They are both equal to 60 degrees, and therefore they are equal to each other. In addition, side OP of the right triangle MPO equals to side OQ in the right triangle NQO, above the radii of the circle is equals to 5, and therefore they are equal to each other. Here it is very easy to see that the moment that OP equals to OQ, because of the fact that those two lines relate OP and OQ, they are both the radii of the circle is equals to 5, and therefore they are equal to each other. So we know that OP in the right triangle MPO equals to OQ in the right triangle NQO. Both the radii of the circle is equals to 5, and therefore they are equal to each other. So again, we can find out that side OP of the right triangle NPO equals to side OQ in the right triangle NQO. Now both the radii of the circle is equal to 5, and therefore they are equal to each other. And finally, those two angles are both equal to 30 degrees, therefore they are equal to each other. So actually this is angle MOQ in the right triangle. So actually angle MOP is angle MOP in the right triangle MPO, and it is equals to this angle, this is actually angle NQO in the right triangle NQO. So repeat again, I shall find out that angle MOP in the right triangle NPO equals to angle NQO in the right triangle NQO. They are both equal to 30 degrees, and therefore they are equal to each other. So actually proved that those two angles on the side that included between those two angles, that is side OP in the right triangle MPO, corresponding equal to those two angles, and side that included between those two angles, that is side OQ in the right triangle NQO. And therefore, actually proved that those two right triangles can go into each other according to angle side angle rule. We have those two angles in the side PO that is included between those two angles are correspondingly equal to those two angles, and the side that is included between those two angles, that is side QO and right triangle NQO. And therefore, those two right triangles can go into each other according to angle side angle rule. So I write it down. We found out that the right triangle NQO congruent this is the sign of congruent to the right triangle MPO according to angle side angle rule. And from the fact that triangle MPO can go into triangle NQO, we derive that the right triangle also have the same areas. That is to say, we derive that the area of the right triangle NQO is equal to the area of the right triangle MPO. Repeat again, because of the fact that triangle NQO can go into triangle MPO, we derive that they have also the same areas. That is to say, the area of the right triangle NQO is equal to the area of the right triangle MPO. So this is equation 1. But because of the fact that the area of the right triangle NQO consists of, here we define this point as point S, So because of the fact that the area of the right triangle NQO, or the right triangle NQO, this right triangle NQO consists of two small right triangles. It consists of the right triangle, this right triangle and the right small triangle NSO, and it also consists the small right triangle OSQ. And therefore, the area of the right triangle NQO must be equal to the area of the small right triangle NSO plus the area of this right triangle SOQ. So it is known the area of the right triangle NQO equals to the area of the small right triangle NSO plus the area of this small right triangle OSQ. Repeat again, because of the fact that triangle NQO consists exactly the two right triangles NSO and triangle OSQ, it means that the area of the right triangle NQO must be equal to the sum of the areas, to the sum of the two small triangles that triangle NQO consists of. And therefore, in total, we can find out that the area of triangle NQO is equal to the area of the small triangle NSO plus the area of the small triangle OSQ. And according to equation 1, the area of triangle NQO equals to the area of triangle MPO. But because of the fact that this is triangle MPO consists of this green quadrilateral MPSN, and also it consists of this small right triangle NSO. And therefore, the area of this right triangle MPO must be equal to the sum of the areas of quadrilateral MPSN plus the area of this small right triangle NSO. So write it down. In total, we should find out that the area of the right triangle MPO is equal to the area of quadrilateral MPNS plus the area of this small right triangle NSO. Repeat again. Because of the fact that the right triangle MPO consists of exactly quadrilateral MPNS and also the small right triangle NSO, it means that the area of the right triangle MPO must be equal to the sum of the areas that it consists of. That is to say, the area of quadrilateral MPNS plus the area of the small right triangle NSO. So this is equation 1. So in this equation 1 we have the area of triangle NSO in both sides of the equation. So the area of triangle NSO will get cancelled. That is to say, we subtract the area of triangle NSO for this equation, equation 1, and therefore the area of triangle NSO will get cancelled, and we left only with equation 1, we left only with the area of triangle OSQ is equals to the area of quadrilateral MPNS. Again, I shall find out that the area of triangle OSQ is equals to the area of quadrilateral MPNS. So if we define the area of this quadrilateral the green quadrilateral MPNS SA, then the area of this triangle OSQ must be also equal to A, because of the fact that according to equation 1 they are equal to each other in their areas. So if the area of quadrilateral MPNS is A, then the area of this triangle OSQ must be also equal to A. Our mission is to find out the area of this green shape. So what is the area of the green shape? The area of the green shape from the lines is very easy to see that the area of this green shape equals to the area of second quadrilateral MPNS plus the area of shape SPQ. This shape, green shape SPQ. This again, the area of the green shape in total equals to the area of this quadrilateral, green quadrilateral MPNS plus the area of this green shape PSQ. But we have already found out that the area of quadrilateral MPNS equals to the area of triangle OSQ. Therefore, we can substitute the area of quadrilateral MPNS in this equation by the area of triangle OSQ. We do it now, we get that the area of the green shape in total is equal to the area of quadrilateral MPSN. Here, they are both equal to A in their areas, and therefore we can substitute the area of this green quadrilateral MNSP by the area of this triangle OSQ, that is also equals to A square units in its size. So we substitute the area of the green quadrilateral MPNS by the area of this triangle OSQ. And we have plus the area of shape SPQ plus the area of this green shape SPQ. But from the drawing it is very easy to see that the area of this triangle SOQ plus the area of this green shape PSQ in total it is equal to the area of sector POQ. Repeat again, the area of this triangle OSQ, the green triangle OSQ plus the area of this green shape PSQ in total it is equal to the area of sector POQ. Okay. So it is equal in total to the area of sector PSQ. But what is the area of this sector POQ? Because again, the area of this triangle SOQ plus the area of this green shape PSQ in total it is equal to the area of sector POQ. Okay. Total it is equal to the area of sector POQ. But what is the area of sector POQ? This is sector POQ. What is the area of this sector POQ? The area of any sector equals to pi r squared, that is the area of the circle, times the angle between the legs of the sector, that is 30 degrees over 360 degrees. And again, the area of sector POQ equals to pi r squared, that is the area of the circle, times the angle between the legs of the circle, that is 30 degrees over 360 degrees. The radius r of this circle equals to 5, and therefore r squared is 5 squared. So total pi r squared is 25 pi. Pi r squared is 25 pi. and 30 over 30 degrees over 360 degrees, this is 1 over 12. So in total we found out that this green shape equals to either 25 pi over 12 square units, so in terms of numbers, this green shape is equal to 6.545 square units. So I repeat again, I shall find out that the area that we are looking for in this question, that is the area of this green shape, it is equal to either 25 pi over 12 square units, so in terms of numbers, the area of this green shape equals to 6.545 square units. Okay, so finish the second question. In the next step, I'll summarize the lecture. We start with the first question, of course. Our mission in this first question is to find out the area of this green shape. So, in the drawing, we have square ABCD. We know that this is angle PQC, this is a right angle. In addition, we know that side PQ equals to 2 units in its length. This is side QC, that is equals to 3 units in its length. Again, our mission is to find out the area of this green shape. This is actually the area of the green quadrangle PQCD. So first of all, you know that all the angles in any square are right angles. So those four angles are all right angles. And we know that all the sides in any square are equal to each other. So we define one side of this square ABCD as A, and therefore all the other three sides must be also equal to A units in their length. This is according to our definition. So AD equals to DC equals to CB equals to BA equals to A units according to our definition. In the next step, we define the length of this line segment BQ as X. So what is the length of AQ? From the drawing, it is very easy to see that AQ equals to AB minus QB. Again, AQ equals to AB minus QB. So AQ equals to AB, this is A, minus QB, this is X. So in total, AQ equals to A minus X units instead of AQ equals to A minus X units. In the next step, we define this angle QCB as alpha. So in the right angle QBC, this angle equals to alpha. This angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles in any triangle. AB is one side of square ABCD, therefore it is absolutely a straight line. So AB is a straight line. So if you focus on this side of the straight line AB, it's point Q. Here the sum of the angles must be equal to 180 degrees according to all three that says that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at this side of the straight line AB at point Q? We have this angle that is equal to 90 degrees minus alpha, this angle equals to 90 degrees. And therefore this third missing angle must be equal to alpha. Why? Because alpha plus 90 degrees minus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. That is the sum of the angles on one side of the straight line AB, according to all three. So this missing angle must be equal to alpha. So in the right angle QAP, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha according to the sum rule that says that the sum of the angles in a triangle is equal to 180 degrees. So in the next step, I copied this right triangle AQP and this right triangle QBC in the new page, and we proved that those two right triangles are similar to each other according to angle rule. So actually, those are the two right triangles that are covered from the original drawing. This is the right triangle APQ and this is the right triangle QBC that are covered from the original drawing. So the next step we put that those two right triangles are similar to each other according to angle rule. So why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So in total, we found out that all the three angles in the right triangle APQ, this right triangle APQ are corresponding equal to the three angles of this right triangle QBC, and therefore those two right triangles are similar to each other according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AP on the right triangle APQ over side QB in the right triangle QBC equals to side AQ in the right triangle APQ over side BC in the right triangle QBC, and it is also equals to side PQ in the right triangle APQ over side QC in the right triangle QBC. AP is the missing side, so we leave it as it is. QB is X, AQ is A minus X, BC is A, PQ is 2, and QC is 3. So in total, according to equation 1, we shall find out that AP over X equals to A minus X over A, and it is also equals to 2/3. Those two sides are equal to each other, therefore we can get equation 1 from those two sides that are equal to each other. So according to equation 1, we shall find out that AP over X equals to 2/3. This is equation 1. Here we multiply this equation 1 by X, and finally found out that AB equals to 2/3 times X. This is according to equation 1. We note that those two sides are equal to each other. So therefore we can get equation 2 from those two sides that are equal to each other. That is to say, according to equation 2, we shall find out that A minus X over A equals to 2/3. This is equation 2, A minus X over A equals to 2/3. Here we cross multiply this equation, equation 2, and finally found out that 3 times A minus X equals to 2A. Here we open the brackets on this hand on this equation, equation 2, and finally found out that 3A minus 3X equals to 2A. Here we subtracted 2A from this equation 2, and finally found out that 3A minus 2A is A, minus 3X equals to 0. Here we added 3X to this equation, equation 2, and finally found out that A equals to 3X according to this equation 2. According to equation 1, we have already found out that AP equals to 2/3 times X. In the next step, I copied this right triangle QBC in the new page and implemented the Pythagoras theorem on this right triangle QBC. So okay, this is the right triangle QBC that is copied from the original drawing. According to the Pythagoras theorem, is this right triangle QBC, QC squared, that is the square of the hypotenuse, is equal to QB square plus BC square. QC is 3, therefore QC square is 3 squared, that is 9, plus QB square. QB is X, therefore QB square is X square, plus BC square. BC is 8, therefore BC square is A square. So in total, according to equation 3, I shall find out that 9 equals to X square plus A square. This is according to equation 3, while according to equation 2, we have already found out that A equals to 3X. If A equals to 3X, it means that A squared must be equal to 3X squared. And therefore, we can substitute A squared in this equation 3 by 3X squared from this equation 2. We did it, and we should have found out that 9 equals to X squared plus A squared. And A squared, according to equation 2 is 3x squared. So in total, according to equation 3, I should have found out that 9 equals to x squared plus 3x squared. So 9 equals to x squared and 3x squared is 9x squared. So in total, I should have found out that according to equation 3, 9 equals to x squared plus 9x squared. X squared plus 9x squared is 10x squared. So in total, according to equation 3, I should have found out that 9 equals to 10x squared. Here we divided the equation 3 by 10 and finally found out that x squared equals to 9 tenths. According to equation 3, we found out that x squared equals to 9 tenths. Here we took out of this equation and finally found out that x equals to the square root of 9, that is 3, over square root of 10. But again, according to equation 3, we found out actually that x equals to 3 over square root of 10 units in its length. According to equation 2, a equals to 3x. So a equals to 3 and x is 3 over square root of 10. So in total a equals to 3 times 3 over square root of 10. 3 over 3 is 9, so in total this expression equals to 9 over square root of 10 units in its length. So in total we can find out that a, that is the length of one side of square ABCD, is equal to 9 over square root of 10 units. Okay, again, this is side DC that is equals to a, and a equals to 9 over square root of 10 units in its length. The only thing that is left to find is to find out the length of this missing line segment AP. And according to equation 1, we have only found out that AP equals to 2/3 x. So AP equals to 2/3 times x, and x is 3 over square root of 10. So in total we found out that AP equals to 2/3 times 3 over square root of 10. But we have 3 in the numerator and 3 in the denominator, so 3 will get cancelled. After we cancelled 3, we should found out that AP in total equals to 2 over square root of 10 units in its length. This is line segment AP that equals to 2 over square root of 10 units in its length. What is the length of this missing line segment PD? From the drawing it is very easy to see that PD equals to AD minus AP. Okay, again, PD equals to AD minus AP. So PD equals to AD is A, minus AP. We just found out that AP equals to 2 over square root of 10 units in its length. So in total PD equals to A minus 2 over square root of 10 units in its length. But we already found out that A equals to 9 over square root of 10. So PD equals to A, and A is 9 square root of 10 minus 2 over square root of 10. So in total PD equals to 9 over square root of 10 minus 2 over square root of 10. 9 over square root of 10 minus 2 over square root of 10 is 7 over square root of 10. So in total we found out that the missing 97 PD is equal to 7 over square root of 10 units in its length. Our mission is to find out the area of this crane shape. So in the next step we join points P and C together by straight line. By joining points P and C, we can adhere those two right angles, the right angle PDC and this right angle PQC. And because of the fact that the green shape consists exactly those two right angles, it means the area of the green shape must be equal to the sum of the areas of those two right angles that the green shape consists of. That is to say, in total we shall found out that the area of this green shape equals to the area of the right angle PDC plus the area of this right angle PQC. Repeat again. In total we found out that the area of the green shape equals to the area of the right green triangle PDC plus the area of the right green triangle PQC. What is the area of the right triangle PDC? The area of the right triangle PDC equals to the base of the triangle that is PD times the height that is DC over 2. Repeat again, the area of the right triangle PDC equals to the base that is PD times the height that is DC over 2. Plus the area of this right triangle PQC. The area of the right triangle PQC equals to the base that is PQ times the height that is QC over 2. Then again, the area of the right triangle PQC equals to the base that is PQ times the height to the base that is QC divided by 2. PD is 7 over square root of 10 times DC that is A, and A is 9 over square root of 10 divided by 2. So in total, the area of the right triangle PDC equals to 7 over square root of 10 times 9 over square root of 10 divided by 2. Plus the area of the right triangle PQC. That is, PQ is it is PQ times QC over 2. PQ is 2, QC is 3 divided by 2. 7 times 9 is 63, square root of 10 times square root of 10 is 10, so in total this expression equals to 63 over 10 over 2. 63 over 10 over 2 plus the area of right triangle PQC, that is 2 times 3 over 2. 2, we have 2 in the denominator and 2 in the denominator, so 2 will get cancelled, and we left only with 3. And here we have 63 over 10 over 2 is 63 over 10 times 2. So it is 63 over 10 times 2. 10 times 2 is 20. So in total this expression equals to 63 over 20 plus 3. So here we multiplied 3 by 20 and then we divided by 20 in order to come out of this number. So in total we have the ratio equals to 63, and 3 times 20 is 60, so it is 63 plus 60 over 20. 63 plus 60 is 123 divided by 20. So in total we should find out that the area of this ring shape equals to either 123 over 20 square units, so in terms of numbers, the area of this ring shape equals to 6.15 square units. Okay, so we finished with the first question. In the next step, I presented to you the second question and we solved it. So finally, in the second question, our mission is to find out the area of this ring shape. So in the drawing, we have quarter circle AOB. We know that arc AP equals to arc PQ equals to arc QB. In addition, we know this is again AOB, this is right angle. Those two angles are also right angles. And we also know that OB equals to 5 units in its length. That is to say, the radius of this quarter circle is equal to 5 units. Again, our mission is to find out the area of this green shape. Because of the fact that arc AP equals to arc PQ equals to arc QB, we can implement the rule 20. So repeat quickly rule 20. According to rule 20, in front of equal arcs, there are equal center angles. So in the drawing, we have a circle. And we also know that this is arc AB, that is equal in its length to this arc CD. And therefore, according to this rule 20, in front of those two equal arcs, we have equal center angles. So those two center angles that are located in front of those two equal arcs must be equal to each other. That is to say, center angle alpha equals to center angle beta, or alpha equals to beta. So in front of equal arcs, we have equal center angles. In front of those two arcs AB that is equal to CD, we have those two angles that are also equal to each other. Those two center angles that are equal to each other. That is to say, alpha equals to beta. So we can actually implement all 20 in our drawing. In our drawing, we have arc AP equals to arc PQ equals to arc QB. And therefore, in front of those two equal arcs, we have equal center angles. That is to say, those three angles, 1, 2, 3, they also must be equal to each other in their sizes. So if this angle is x, then the other two angles must be also equal to x, because they are equal to each other according to rule 20. So if this angle AOP is x, then this angle, center angle P or Q must be also equal to x, and this center angle Q or B must be also equal to x. So all those three center angles, each of them is equal to x according to rule 20. But it is very easy to see that the sum of those three center angles equals to the big angle AOB. That is to say, x plus x plus x equals to angle AOB. But you know that angle AOB equals to 90 degrees, because AOP is a quarter circle. And therefore, in conclusion, actually found out that 3x, that is the sum of those three center angles, is equal in total to 90 degrees. 3x equals to 90 degrees. We divided this equation by 3 and finally found out that x equals to 30 degrees in its side. So this is angle x, that is 30 degrees. This is also angle x, that is 30 degrees. And this is angle x, that is equals to 30 degrees in its size. So in the right triangle MPO, this is the right angle MPO. This angle equals to 30 degrees. This angle equals to 90 degrees. Therefore, this first angle must be equal to 60 degrees in its size, according to the rule that states that the sum of the angles in any triangle is equal to 180 degrees. Likewise, in the right triangle NOQ, this big angle MOQ equals to 30 degrees plus 30 degrees, that is 60 degrees. This is the right angle, and therefore this third missing angle must be equal to 30 degrees in its side, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. So, in the next step, I copied this right triangle MOP and this right triangle NOQ in the new page, and we proved that those two right triangles can go into each other according to according to side angle rule. So actually, those are the two right angles that are going from the original drawing. This is the right angle MPO, and this is the right angle NQO that are going from the original drawing. So in the next step, we proved that those two right angles can go into each other according to angle rule. When they can go into each other, first of all, those two angles are both equal to 60 degrees, therefore they are equal to each other. In addition, those two angles are both equal to 30 degrees, and therefore they are equal to each other. In addition, side OP equals to side OQ. They are both the radii of the circle, and therefore they are equal to each other. You can see from the drawings, it's very easy to see that OP is the radius of the circle, that is equal to 5, and OQ is also the radius of the circle, that is equal to 5 units. Again, OP equals to OQ equals to 5. So actually I proved that those two angles and the side that included between those two angles, that is side OP, are correspondingly equal to those two angles, and the side that included between those two angles, that is side OQ, and the right triangle NQO. And therefore, I shall prove that those two right triangles can go into each other according to angle side angle rule. We have those two angles and the side that included between those two angles, that is side OP, that correspondingly equal to those two angles, and the side that included between those two angles, that is side OQ, and the right triangle NQO. And therefore, those two right triangles can go into each other according to angle side angle rule. And from the fact that those two right triangles can go into each other, we will derive that they have also the same areas. That is to say, the area of this triangle MPO is equal to the area of this triangle NQO. Repeat again. Because of the fact that triangle NQO can go into triangle MPO, we derive that they have also the same areas. That is to say, the area of the triangle NQO is equal to the area of the triangle MPO. But this is the right triangle NQO. The right triangle NQO consists of this small right triangle NSO and this small right triangle QSO. And therefore, the right triangle NQO must be equal to the sum of the areas of the two right triangles that it consists of, the two triangles that it consists of. That is to say, the area of triangle NQO must be equal to the area of the two right triangles that it consists of. That is to say, it must be equal to the area of the small right triangle NSO plus the area of the triangle NOSQ. And according to the equation 1, the area of triangle NQO equals to the area of triangle MPO. This is the right triangle MPO. The right triangle MPO consists of the green quadrilateral MNSP, and it also consists of the small right triangle NOS. And therefore the area of the right triangle NPO must be equal to the sum of the areas of the quadrilateral MNSP and the small triangle NSO that it consists of. Repeat again. The area of triangle MPO must be equal to the sum of the areas of the components that it consists of. That is to say, it must be equal to the area of quadrilateral MP and S plus the area of the small right triangle NSO. So here we have a triangle NSO on both sides of the equation 1. So we can subtract the area of this triangle NSO from both sides of the equation. So this the area of triangle NSO will get cancelled, and we left only those two components. That is to say, we actually found out that the area of triangle OSQ is equal to the area of quadrilateral MP and S. This is to say, the area of this quadrilateral MNSP is equal to the area of this small triangle OSQ. So if we find the area of this green quadrilateral MPSNSA, then the area of this triangle OSQ must be also equal to A because they have the same areas. Okay? Our mission is to find out the area of this green shape. From the domains, it's very easy to see that the area of this green shape equals to the area of this green quadrilateral MPSN plus the area of this green shape PSQ. Okay, again, the area of the green shape in total equals to the area of the green quadrilateral MPNS plus the area of the green shape SPQ. But we already found out that the area of quadrilateral MPNS equals to the area of triangle SOQ. Therefore, we can substitute the area of quadrilateral MPSN by the area of this triangle OSQ. We did it. Here, we substituted the area of this quadrilateral MPNS by the area of triangle OSQ, and we have also plus the area of the green shape SPQ. So the area of the green shape in total equals to the area of this triangle SOQ plus the area of this green shape PSQ. Again, the area of the green shape in total equals to the area of the small white triangle SOQ plus the area of this green shape SPQ. The sum of the areas of those two shapes, it is obvious that it equals to the area of this sector POQ. Again, the sum of the areas of those two shapes, in total, it is equal to the area of sector POQ. It is very easy to see that the sum of the areas of those two shapes, it is equal to the area of this sector POQ. So the area of the white triangle OSQ plus the area of the green shape SPQ, in total it is equal to the area of sector POQ. But what is the area of sector POQ? What is the area of this sector POQ? The area of any sector equals to pi r squared. That is the area of the circle that contains the sector times the angle between the legs of the sector over 360 degrees. And therefore, the area of sector POQ must be equal to pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. And again, the area of sector POQ equals to pi r squared times the angle between the legs of the sector, that is 30 degrees, over 360 degrees. The radius of this circle that contains sector POQ r is 5. Therefore, r squared is 25, so pi r squared is 25 pi. Pi r squared is 25 pi. And 30 degrees over 360 degrees, it is 1 over 12. So in total, if we found out the area of this green shape equals to either 25 pi over 12 square units, or in terms of numbers, the area of this green shape equals to 6.545 square units. Okay, thank you very much.